Polymer fractionation. We have seen that in a polymer sample, all the molecules do not have the same molecular weight, and that the sample as such has a certain average molecular weight. The whole sample can, however, be separated into smaller samples, each having a narrower molecular weight distribution of and different average molecular weight of their own. Each of the smaller sample is known as a fraction of the original unfractionated sample. The process of separating the unfractionated sample into several fractions of progressively increasing or decreasing average molecular weight is known as polymer fractionation. From the knowledge of the weights of individual fractions and their corresponding average molecular weight, we can compute the distribution curve of the original unfractionated sample. The pattern of the distribution curve for an unfractionated polymer sample and those for a set of fractions obtainable from it are shown in figure 13.3. So let me explain you what is polymer fractionation. You know, polymer is such a big macromolecule that it has long chains of monomers inside it. So some chains are branched. Okay. So, and it consists of many molecules. So all these molecules do not have the same molecular weight. Suppose one molecule of a polymer of polyvinyl chloride is having a molecular weight of 100, another one is 200, another one is slightly bigger, 300, and then 400, and so on. So now I want to separate this molecules which are having molecular weight 100, then I want to separate the molecules which are having molecular weight 200, because you know I am just talking about there are so many chains in the polymer, and in the chains there are so many molecules. So suppose I want to separate the molecules having 100 molecular weight, and then the molecules having 200 molecular weight, and then the molecules having 300 molecular weight. I want to separate them into different test tubes, for example. So I will have to fractionate the unfractionated sample. So that process is known as polymer fractionation. Hope it is clear to you. The definition by the book is the process of separating the unfractionated sample into several fractions of progressively increasing or decreasing average molecular weight is known as polymer fractionation. So now in this you can see on the x-axis I am plotting the molecular weight, average molecular weight, okay, and on the y-axis I am plotting the weight of the fraction, okay. So on y-axis there is weight, okay, of the, suppose in one test tube you have collected 100 average molecular weight samples, you know, one fraction it is, so the weight of it is plotted on the y-axis and the average molecular weight on the x-axis. So this is way, in this you can see 1 2 3 4 1 2 3 4 5 6 7 fractions he has made of this unfractionated sample, complete one, and he has got this graph. So let's read what it's saying. Pattern of molecular weight distribution curve of an unfractionated polymer sample and those for a set of fractions 1 to 7 obtainable from it. The curve shown in the broken line represents the distribution for the polymer remaining in the solution after successive fractions are removed. So suppose I remove the first fraction like this one. So still there are, suppose I have removed the 100 average molecular weight molecules. So but still there are 200, 300, 400 and 500, 600, 700 average molecular weight still left in the polymer. So they are represented by this dotted line. Then suppose I remove the 200 ones fraction. Still the 300, 400, 500, 600 ones are, because 100 and 200 are removed earlier. Then this 300. Then this dotted line shows distribution for the polymer remaining in the solution after successive fractions are removed. However, before knowing the procedure for computing the molecular weight distribution curve, we should know how to separate the original sample into several fractions. Like suppose I give you a polymer and I told you and I tell you to make fractions of it. So how will you make it? So let us see. We should know how to separate the original sample into several fractions. There are in fact several methods available for this. The most important being fractional precipitation, partial dissolution, gradient elution and gel permeation chromatographic technique. So let us see one by one. The most important being fractional precipitation technique. As the name suggests, there will be precipitation in this technique. When a small quantity of non-solvent miscible with the solvent is added to a polymer solution in a poor solvent, the non-solvent decreases the solvent power further to such an extent that the molecular species of the highest molecular weight can no longer be held in the solution and hence are thrown out of the solution as solvent gel. So suppose I have taken a non-solvent and there is a solution containing solvent and polymer. The polymer is dissolved in the solvent, but this solvent is a poor solvent. So in this solution, if I add a non-solvent which is miscible with the solution, so it will further reduce the solvent power of that poor solvent. At first only it is a poor solvent, then this non-solvent will come and it will further reduce its solubility of the polymer. So what will happen? In the polymer, the highest molecular weight species will be thrown out as a solvent gel first. If the solvent gel is removed and a further quantity of non-solvent is added to the remaining solution, the solvent power is further decreased and the molecular species of the next higher molecular weight are thrown out. So if you read this, you will get it what happens next. Suppose I add now more. Suppose the solid mass I got of the high molecular weight species, I took out that solid mass and then I again add more non-solvent to the solution. So the solvent power of that solubility power of that poor solvent is further reduced now. So therefore the molecular species of the next higher molecular weight means it's second in position to the one which we have just separated. It will be thrown out. Okay. In this way, each time some quantity of the non-solvent is added to a polymer solution, a partial precipitation of the polymer occurs. The fractional precipitation techniques makes use of this principle. So now you understood the principle. The major difference between fractional precipitation, also called partial precipitation. So I can ask this question either by the name of fractional precipitation or by partial dissolution. So I can ask it by fractionation by precipitation or also by partial precipitation. And purification. So what is the difference? The major difference between fractionation, precipitation and purification, because I may have said the same thing in purification also. By precipitation lies in the quantities. So the major difference between the fractionation by precipitation and purification by precipitation lies in the quantities of the polymer solution and the non-solvent taken. So in the former case means in fractionation by precipitation, small quantities of non-solvent are added to a large volume of solution. Like I said, first non-solvent was added, so first higher molecular weight species was thrown out. Then more it was added, then second higher molecular weight species was thrown out. So like this, in this case, fractionation by precipitation, the non-solvent is little and the solution is large. Whereas in the latter case means purification by precipitation, only a small quantity of solution at a time is added to a large volume of non-solvent. So it's opposite of that. The experimental procedure for fractional precipitation is as follows. A 1% solution of a polymer in a poor solvent is taken in a sufficiently large container with provision for stirring and drop-wise addition of the non-solvent. Okay, the whole setup is thermostated so as to maintain the contents at a constant temperature within plus minus 0.01 degrees Celsius. Since dissolution and precipitation are equilibrium processes and sensitive to temperature change, the whole process of fractional precipitation should be carried out at a constant temperature for effective fractionation. That's why we have taken a thermostat. After allowing a sufficient time for the contents to attain the required temperature, the non-solvents are added drop-wise with continuous stirring. As the non-solvent is added progressively, turbidity appears, indicating the precipitation of the highest molecular weight species. Turbidity, and then it settles down. Okay. When sufficient turbidity has been developed, the addition of non-solvent is stopped and the contents are slowly heated till the turbidity disappears. So when the sufficient turbidity has been developed, the addition of non-solvent is stopped and the contents are slowly heated till turbidity disappears. In this heating process, the precipitated polymer get redissolved at a slightly higher temperature, because we know if we increase the temperature, the solubility increases. At this stage, the stirring is stopped and the setup is allowed to cool down to the original precipitation temperature. Now the turbidity reappears. A proper equilibrium between the low molecular weight species in the dissolved state and the high molecular weight species in the precipitated state established, resulting in an effective fractional precipitation. The whole setup is then allowed to stand at a constant temperature for sufficient period of time, say 8 to 10 hours, so that the precipitated polymer fraction settles down in the container as a gel-like mass. So what is happening? So that the precipitated polymer fraction settles down in the container as a gel-like mass. Okay. The gel is carefully separated by siphoning without disturbing the supernatant clear solution. So what is siphoning? Siphoning is taking one material from one container into another with the help of a tube. After the gel has been removed, a fresh lot of non-solvent is added to the clear solution till turbidity appears, and the whole sequence of operation is repeated till the second fraction is separated. By repeating the process several times, we can collect several fractions. So in this way you can collect the fractions. We can collect several fractions. The last fraction, however, is generally recovered by simply evaporating off the non-solvent solvent mixture. There are several modifications to the precipitation technique. One such method of fractional precipitation involves the cooling of the polymer solution in a single solvent The method is very simple. The solution is made at an elevated temperature, say 80 degrees Celsius, and then slowly cooled and maintained at a lower temperature, say 75 degrees Celsius, for some time. Now the highest molecular weight species are thrown out of the solution and are carefully removed. The solution is further cooled slowly and maintained at a still lower temperature, say 70 degrees Celsius, when the second fraction gets precipitated. Okay, the process is continued till several fractions are obtained. The drawback of the process is that in case of some polymers, simple cooling does not precipitate the polymer. Yet another way of fractional precipitation is by solvent volatilization. The polymer is dissolved in a binary mixture of solvent and non-solvent. The solvent-non-solvent system is chosen in such a way that the solvent is highly volatile compared to the non-solvent. By inducing a slow suction of vapor phase above the polymer solution, the solvent slowly evaporates. The solution therefore becomes progressively richer in non-solvent. Hence, the polymers start precipitating out, the high molecular weight species being thrown out first. By controlled evaporation of the solvent and intermittent collection of the polymer precipitated, several fractions can be separated. So now you understood this. First, this is the heating one. First you heat. So what happens? All the high molecular weight species also get dissolved at elevated temperature, but as soon as you reduce the temperature to 5 degrees, the high molecular weight species get thrown out. Then you separate it by siphoning. Then again you cool it further. Then second higher molecular weight species separates out. That's how the fractionation is done. And then finally, yet another way of fractional precipitation is by solvent volatilization. So the polymer is dissolved in the binary mixture of solvent and non-solvent. So what happens? The solvent-non-solvent mixture is chosen in such a way that the solvent is highly volatile compared to the non-solvent. Okay, so you choose such a system of binary mixture where the solvent is more volatile than the non-solvent. So in this, you just induce a slow suction of the vapor phase above the polymer solution. So slowly that suction of vapor phase makes the solution to evaporate, and then the quantity of non-solvent increases in the solution. Hence the polymer starts precipitating out. So as usual, higher molecular weight species are being thrown out first. By controlled evaporation and solvent of the solvent and intermittent collection of the polymer precipitated, several fractions can be separated. Okay. Now, partial dissolution extraction technique. The partial dissolution technique is based on the fact that polymer solubility in a solvent is restricted depending on the solvent power by its molecular weight. Okay. So higher the molecular weight, lower the solubility, lower the molecular weight, higher the solubility. A poor solvent can therefore dissolve only low molecular weight species, whereas good solvent can dissolve higher molecular weight species too. Yeah, because solubility in a solvent is restricted depending on the solvent power by its molecular weight. Yeah. If we have a series of solvents with increasing solvent power, okay, so in one test tube I have taken a poor solvent, then next to it slightly stronger solvent, then next to it slightly stronger, and then finally a strong solvent or a good solvent. By using each solvent separately and starting from the one with the lowest solvent power, we can dissolve the fractions of different molecular weight one after another, starting from the lowest fraction. So we can dissolve the fractions of different molecular weights one after another, starting from the lowest fraction. Because we have arranged it in an ascending order, so the lowest one will be dissolved in the poor solvent, then a little bit higher in the next and next, and so on. So this is how also you can get fractions of polymer by partial dissolution technique. The experimental procedure can be outlined as follows. The polymer sample to be fractionated is taken in the form of fine powder or as small pieces, as small as possible. A series of solvent mixture with increasing solvent power is developed by using different porosity grades. Okay, so now there is a problem. In this PDF there is a page missing, so we have to use the book now. So a series of solvent mixture with increasing solvent power is developed by using binary mixtures comprising the solvent and non-solvent in different ratios. It should be noted that the mixture having the lowest solvent to non-solvent ratio will have the least solvent power, and the one having the highest ratio will have the highest solvent power. Next, the binary mixture of the lowest solvent power is added to the powdered polymer sample. The polymer sample is allowed to swell fully, and then the entire content is stirred well to enhance the process of dissolution of the lowest molecular weight species in the solvent mixture. Depending on the quantity of the polymer taken, the stirring time should be adjusted to achieve the complete dissolution of all the soluble components. At this stage, the stirring stopped, the solution filtered off, and the filtrate collected. The first fraction is recovered completely by evaporating the solvent from the filtrate. To the solid mass left and dissolved by the first lot of the binary mixture. The binary mixture with the next higher solvent power is added and stirred. The whole process is repeated till second fraction is recovered. In this way, by successive dissolution with binary mixtures of increasing solvent power, the series of fractions with increasing average molecular weight can be separated. So that's it. Now gradient dilution technique. So gradient dilution technique and gel permeation chromatographic techniques, these two are your assignments.